would like to come to ask you to come forward and to take the position behind the lectern. After all handles, you are ready?
Yes.
Yes, thank you very much. And it's my pleasure to invite your first promoter, Professor De Wit, to start the proposition.
Dank u wel, meneer de rector. Hartelijk awareness. The usual question, 4 years hard work, just 10 minutes to explain the key issues of your work.
For the later promoter, I will start explaining by giving a short presentation. The title of my PhD dissertation is Quantitative Nanoscopy of Conductive Hierarchical Materials. Let me explain hierarchical materials first. Hierarchical materials are made of small building units of materials which forms an organized structure at increasing length scales. For instance, in this case, you can see a carbon nanomatrix based polymer matrix is one such example of hierarchical materials and forms an organized structure and unleashing functional properties like thermal stability, mechanical rigidity, and electrical conductivity. These functional properties are intimately depends on these multi-scale network, starting from the nanoscale contacts via the mesoscale structure to the functional properties. In order to understand and study these materials, multi-scale information of these from the lower length scale to the higher length scale is required. This makes the multi-scale characterization very critical. In general, materials are characterized by scattering as well as microscopy techniques. Scattering has a specific advantage that it can probe very large volume, so it gives the representative results. However, the problem is they give the average description of the material. So if a material is, in order to study the multi-component system or the polydispersed system, we need a specific model. But models about the multi-component system and the polydispersity, these kind of models are very difficult to incorporate in the analysis. In that case, microscopy gives the direct local analysis of these kind of specific features. However, in microscopy, sampling is a big issue. Because of the limited size of the STEM detector and the CCD cameras, it always questions the representability of the microscopy data. So the goal of my thesis is to create a multi-scale calibration tool based on the electron microscopy to obtain the representative volume and then relate it to the functional properties. In order to identify and obtain the representative volume, we need 3 modules of the multi-scale calibration tool, starting with contrast optimization, large area imaging, and quantitative image analysis. Let me explain contrast optimization in STEM imaging. In STEM imaging, a focus probe of electron scans on the sample, and the transmitted scattered electrons are detected by the annular detector. By changing the distance between the specimen and the annular detector, we can collect the electrons scattered at specific angles. For instance, by increasing the camera length, the distance between the specimen and the annular detector, we can collect the bright field. We can detect the direct beam, and which gives the bright field image. By decreasing the camera length, we can detect the highly scattered electron, which gives the dark field image. Somewhere in between these two, you will get the optimum contrast. So in order to identify this optimum contrast, we carried out Monte Carlo simulation. Here, the contrast itself is defined as the difference in the fraction of the electrons scattered by CNT and the carbon nanotubes. For instance, here you can see the peak point, and this shows the high contrast region and the corresponding camera length where you obtain the high contrast region. And one more thing we can notice is, by increasing the section thickness, we can see the overall contrast decreases and the high contrast region also shifts to the right. This is mainly due to the multiple scattering and the beam broadening effect. In order to validate this Monte Carlo simulation, we carried out experiments also, and which matches closely with the experiments. So overall, this simulation toolbox can be used as a predictive tool to identify whether the experiment is possible or not, and also mainly to identify the high contrast region. And this toolbox is more generic. It's not just limited to carbon nanotubes polymer system. It can be applied to any material of our own interest. The next step in the multi-scale characterization tool is the sampling limitation. Sampling limitation can be tackled by imaging large volumes of data. The large volume itself can be acquired by imaging thick sections as well as imaging large areas. Large area imaging with a higher resolution can be effectively obtained by automating the image acquisition process. We automated the image acquisition process by moving the stage automatically, which acquires image sequentially, like shown in this figure, and with a little overlap and stitch the image together and obtains the large area map with a high resolution. For instance, in this case, we can see a typical polymer sample where with the multi-layer polymer, with the HDP layer and PP layer, they are arranged perfectly with a regular spacing. However, on a large-scale map, we can also see the flow defects. We can also see the irregularity in the spacing. And more importantly, this large-scale analysis gives you how the layers itself from the regular spacing is changing to the irregular spacing. With appropriate quantitative image analysis, we can also identify the waviness of these layers. With this, the multi-scale characterization tool completes, starting from contrast optimization, tackling sampling limitation, and quantitative image analysis. With this toolbox, now I'm going to study about the carbon nanotubes, packing, and the electrical conductivity. First example, we chose to study about random packing of polydisperse carbon nanotubes. Here, the carbon nanotubes network itself fabricated, prepared by appropriately mixing the dispersed carbon nanotube dispersion and vacuum filtering them. The global packing analysis of these prepared carbon nanotubes matches closely with the macroscopic plots of the same aspect ratio, and this shows the continuity of the 6 orders of magnitude in the packing phenomena. However, measuring the electrical conductivity shows that optimized network for the electrical conductivity at certain specific aspect ratios. With the use of quantitative image analysis, we try to identify how the network works. In case of the low aspect ratio, because of the large number of contact points, the contact resistance plays a massive role, and the electrical conductivity decreases. However, increasing the amount of the longer tubes forms the global packing, and the short tubes forms the conduction knots. At a specific composition, the resistance of these conduction knots under the connecting long CNTs gets optimized and gives you the higher conductivity. Another example is process-dependent electrical conductivity of carbon nanotubes. Here we can see the electrical percolation curve of the carbon nanotubes composites prepared with the different processing methods. The solvent casting shows the lower percolation, the blue curve, and the red curve, the extrusion, shows the higher percolation. Qualitatively, we found that the qualitative analysis of the image almost looks similar. However, in the solvent casting system, we found that there were large amount of free spaces. Quantitative image analysis revealed 47% of free spaces, that is 47% of the polymer do not have any carbon nanotubes. And in case of the extruded system, it is 13%. So we carried out based on these results, we derived electrical conduction mechanism. In case of solvent casting, during the solvent casting process, because of the local aggregation, these free spaces are created. At the same time, it increases the effective volume fraction in other regions. And this inhomogeneous network is destroyed during the extrusion process, and it forms almost a random network. By the compression molding process, the overall electrical conductivity is further increased. With these examples, I believe I have shown that multi-scale morphology can be tuned particularly for the carbon nanotube network to optimize the electrical conductivity, to realize these multi-scale morphology and the network. We need multi-scale characterization tool, and we implemented it. Along with the quantitative image analysis, I believe, or I claim that this electron microscopy is becoming towards a bulk characterization tool. And I believe this will be the standard technique for the next generation, as it has the capability for the 3D analysis also. Thank you.
Thank you very much for your concise overview.
Dank u wel, Elizabeth. Thank you very much. And it's my pleasure to welcome the external members of the committee, Professor Pasquale from Rice University, Professor van Schaltert at the University of Utrecht, and Professor Philipsen also at the University of Utrecht. Welcome, much appreciated that you took the time to come to Eindhoven and participate in this committee. It's my pleasure to invite Professor Pasquale now to continue the proposition.
Geachte pro-members, I would like to ask you to talk a little bit about the percolation. You use nanotubes that are relatively short. I think your aspect ratios were in the maybe about to 50, 60. And I would like to ask you to discuss whether you think that these results will go all the way to very high aspect ratios, or maybe there may be some different physics.
Colleague opponent, thank you for your question. And yes, the aspect ratio plays a very important role, particularly in case of the composites which I'm preparing. For instance, in the chapter 5, page number 139, I've shown the percolation curve processed by different methods. And here the aspect ratio is 137, I believe, roughly 140. Of course, if I use a different carbon nanotube which is having a higher aspect ratio, the percolation is further going to decrease. But yes, if I'm using a smaller aspect ratio, it is going to increase. That is just specifically based on aspect ratio. But to explain more about that, in case of extrusion, people believe that extrusion would reduce the aspect ratio of the carbon nanotubes itself because of the shear involved. It cuts the carbon nanotube. Maybe that could be one of the reasons that I'm getting the higher electrical percolation. But still, during the extrusion process, I'm doing a very low shear rate, and at the same time, I also measure the aspect ratio before and after extrusion. It is almost similar. So I believe the aspect ratio is not influenced in my curve, but in general, using a high aspect ratio will give you the better conductivity, low contact resistance, and all these.
Thank you. Another question I have is the effect of any pre-bending that the nanotubes may have, and the effect of the stiffness or flexibility of the nanotubes. How do they influence your finding?
Yes, the defects plays an important role. If there are defects in the carbon nanotubes, it is going to affect the electrical conductivity for sure. But in my case, what I'm doing is I'm using the same batch of carbon nanotubes for the different analysis. So I assume that whatever defects is there in my one set, it is going to be there on my second set also. So I'm not taking care of the defect in the first place. And number two, about the flexibility and the tortuosity, which you asked. Yes, it plays an important role, particularly in case of percolating threshold. I believe that if you have a tortuous CNTs, that is going to increase the electrical percolation. And in my case, in chapter 4, I prepared some CNT compacts where my CNT population is completely tortuous. In that case, although the packing was almost close to the non-tortuous straight rods, but I found that because of the tortuosity, the porosity is going to increase a little bit. It is going to increase, it is going to show a big influence. But then, other than that, it also depends on how much tortuous the factor is involving. But in my case, the CNTs are tortuous, but not to massive extent, I believe. So that's why it is close to the straight rods. So in my case, I think I can neglect that.
Thank you. And I'd like to ask you another question more about the technique and how it could be applied in the future. I think it's a very interesting technique, and as one looks at the thinner and thinner carbon nanotubes all the way to single wall, do you think it's going to be applicable as it is, or are there going to be some challenges, both in terms of imaging, but also in terms of, as you made the point, that collecting a large sample size at the appropriate resolution is important. It'd be interesting to understand your point of view on how this could be carried forward.
In general, that is the biggest challenge of my thesis itself. How do you image carbon materials? Carbon nanotubes is also carbon, your polymer is also carbon. So irrespective of whatever your imaging you go, you get the low contrast. And when you go for the single wall carbon nanotubes, the problem is further increased because the single wall carbon nanotubes are something like 2 nanometer or 3 nanometer, maximum 5 nanometer of the diameter. So it is very difficult, but it is not impossible. As I have shown in my chapter 2, I have done image analysis of the single wall carbon nanotubes of the spin coated system. If you see page number 93, where we have the carbon nanotubes and we have the polymer latex particles also, and which is spin coated. And we carried out in the image analysis part lots and lots of steps, starting from filtering and thresholding, top hat filtering, and all these filtering, page number 93. So it is difficult, but it is not impossible, I would say. But at the same time, it also has some kind of a segmentation error involved in it. So it also depends on how much accurate results you want. So I would say it is possible, but I don't say that it is very difficult to do. It also depends on different materials. In single wall carbon, yes, we can do it.
It's actually for the contrast, I'd like to follow up a little bit and ask whether it would be easier if a single wall carbon nanotubes are empty or filled with gas. Would it make it easier?
You mean inside the single wall carbon nanotubes? I believe that doesn't, I would be happy if there is a gold or some metal particles inside the carbon nanotubes, which makes the segmentation much easier, but that is not the question we are answering. So I can just need to press a few buttons for that thing, but what I'm talking is vacuum. There is nothing inside the single wall carbon nanotubes. Even the polymer doesn't go inside the single wall carbon nanotubes. So yes, so if there is something, yes, I can make the process. It is much easier to carry out.
Okay, but having vacuum or a gas will not make it easier.
Will not make it easier. It is vacuum.
I have no further question.
Thank you very much, Professor Gnanasekaran, for your question. Thank you. It's now Professor Philipsen who will continue the conversation.
Thank you. Geachte promovendus, first my congratulations with your thesis, which I read with great interest. It's a well-written thesis and it clearly displays your experimental as well as other skills. I would like to discuss with you a little bit chapter 4, and starting with page 105, the last 1 or 2 sentences, where we read that the aspect ratio was calculated from the weight averaged length divided by the diameter. And I found this sentence at various places in your thesis that you use a weight average of the length, but I couldn't find any explicit reason why you choose a weight average of the length. Could you mention that reason?
Weight component. Thank you very much for your question. Yes, I I calculated the weight average length and diameter because my population, the CNT population which I'm using is polydispersed. So there are many short CNTs and there are many long CNTs also. So I want to give, in the volume fraction, if I'm using long CNTs, so I believe that they have more volume than the short CNTs itself, because at the end what we are talking is a volume, how much volume we are adding the short CNTs, how much volume we are adding the long CNTs. So I want to give weight for that is the main reason why I've gone for the weight average, not the number average
Okay,
calculation.
I was thinking of something different because you measure the packing densities of the carbon nanotubes.
Mm-hmm.
So you like displayed in figure 4.4, and my argument would have been since it is the excluded volume of the randomly oriented tubes that determines the packing density, and realizing that the excluded volume of a thin rod is the diameter times the length squared, I thought that was the reason for using the weighted average because of the length squared and the excluded volume.
Yeah.
Would you agree with that?
I would agree with that, but that was not the first reason why I chose to measure like that. Because I'm in my other chapters also, I'm doing the weight average mainly because of this reason, because the excluded volume effects and these packing itself, what I'm doing is only on chapter 4. So that was the main reason why I chose to do the weight average.
Then on page 105 you also mention that for the length, still talking about the length, you take the end-to-end distance of these rods as depicted in figure 4.1. Now, I thought that if you are looking at packing densities of these sort of semi-flexible objects, I would have more chosen for the persistent length of the semi-flexible object as the relevant length for determining the packing density. Do you agree with that, or were there other reasons why you insisted on using the end-to-end distance as a length measure?
The main reason why I went for the end-to-end distance is because that needs to be correlated with the other analysis also. In page number, in my image analysis, what I'm doing is measuring the end-to-end distance of the agglomerates. So when I'm doing the end-to-end distance of the agglomerates, what I'm seeing is a 2D image of a 3D projection of the 3D rods itself. So there, what I exactly measure is just end-to-end distance of, even if the rods are tortuous or whatever curvy, what I'm measuring is only the end-to-end distance of that. So I'm relating that to the length. So that is the main reason in my first case, like first characterization of the length and the diameter, I went for the end-to-end distance. Of course, I agree.
I understand that, but
Yeah.
Why would you then also use that length measure in, for example, figure 4.4?
Yeah, I'm coming there.
And could you also, do you know the persistent length of these, let's say, of the tubes with the label C? I think these are the longest tubes.
Mm-hmm.
Do you know what the persistent length is?
The length which is straight, which is measurable, or by using a arc length measuring the entire length of the tubes.
No, persistent length.
Is persistent length is just the measurable length of the Yes, the measurable length. Yes, I didn't do like that.
Okay.
I mean, of course, we can do it, but I'm not sure how much difference is going to make in the final.
We'll leave it at that, and then I would like to come to my last question. In figure 4.4, you show quite surprisingly that, at least it appears to be the case, that the density of the mixtures, I have figure 44, page 108, that the packing density appears to be independent of the size of the length distribution. Could you, I mean, do you think that's a sort of coincidence, or do you have an explanation why that is the case?
Yes, I have an explanation. I mean, on the page, on the same page, in the fourth line, you can see that I have mentioned that using polydispersed spheres or bidispersed counterparts, people have shown that it forms the more dense packing than, but I'm getting opposite to that. So,
What you see is that there's no change in density.
no, what I'm saying is like when you're using a polydisperse, the density you get much higher volume fraction density than the monodispersed one.
But that's not what I
Yeah,
see.
that's not what I'm getting. Yeah, that's what I'm saying. That's not what I'm getting. So what I believe is that
So
most
why,
of the
why do you think
packing,
that's the case?
most of the packing itself influenced by the average volume or average length of the carbon nanotubes, not by the polydispersity. So that is what I believe.
Yes, but
And
my-
I found
my
that
question is, why is that?
because in my preparation itself, it could be due to the preparation, how I'm preparing the sample, because in my preparation itself, I found that these small rods are getting sedimented, some of the small rods are getting sedimented, and the overall packing is only by the long rods.
Okay.
So that is the main reason I believe that.
Okay, you say it's an experimental issue.
Yeah.
I think that might be the case, but I think the issue is in the contact number. You measure contact number on average about 10 for your mixtures, and that's the same contact number as one also finds for monodispersed rods.
Yeah.
And maybe if you look at the time very shortly, that number of 10 is 10 because 10 is the number of contacts you need on average to arrest a rod, to keep it in a stable arrested state. And that number is independent of the length of the rod. Because if you have a broomstick and you grab it with two hands, and if you make the stick longer, nothing changes. So that means that for every species in your mixture, the product of the volume fraction and the aspect ratio is 10 divided by 2 is 5. That's for every species. That means that also the average of the volume fraction times the aspect ratio is also 5. And that's from homework for you. And from that you can show that the volume fraction is that 5 divided by the aspect ratio, but the aspect ratio is the weighted average. Exactly the weighted average you were using in the first place. And I think that's the explanation why the density of mixtures is independent of the sizes, of the length distribution. Could you agree with that?
I could agree with that, but what I want to say here is that the C, the coordination number, what I measured here, is not an experimental measure. I cannot measure that experimentally.
No,
But that is itself is derived from the volume fraction and the aspect ratio.
no, you don't have to measure it because it's that C extent has been measured for other systems, and has been also coming from computer simulations. And there's also a calculation for it, so that 10 is robust, so you don't have to measure that.
Okay.
Thank you for your time. Thank you for the discussion.
Okay. Thank you.
Thank you very much, Professor Philipsen, for your questions. It's my pleasure now to invite Professor van der Schoot to continue the conversation.
After Movendus, let me first congratulate you with the finalization of your thesis, which I read with great interest. I do have a few queries though, I'm afraid. The first one connects to what Professor Philipsen has been asking about, which is